I mean, it's not the boring anyway. Yeah, let's start.
Yeah, let's start.
Hello, CoRL. I think we're going to start while people come in. The first few slides are Francesco's and very boring, so it doesn't matter if they miss them. I'm Yuval Tassa. This is Francesco Nori. We're from DeepMind Robotics, and we'll talk to you a little bit about open sourcing projects from DeepMind. Take it away.
So yeah, we thought that as a sponsor talk, it was good to give you an idea of what we are bringing back to the community in the form of open source project. And it's also a nice follow-up from what we've seen last year when Yuval presented the brand new acquisition of MuJoCo. I'm Francesco. I'll be presenting the first part, which is more about our mission, where we're going and why we're doing it. The mission is the statement of solving intelligence to advance science and benefit humanity, which is very general. So I really wanted to bring in a little bit of additional knowledge to understand what we mean by that. First of all, intelligence for us is the ability to perform well in a wide variety of environment. So we will focus more on general intelligence versus more narrow intelligence. And along this line, we think at AI as a science, as a core science that we investigate on, but also as AI as a tool for science. In terms of AI for science, as a science, we have been applying different kind of core investigations on different domains. You see a few examples here. Go is a classical one. StarCraft as a partial information game was a follow-up of that. And more recently, we're interested in bringing AI tools and our discoveries into more grounded simulation of reality as the playhouse. On the other side, we believe that AI can be used for science. And I think you might be aware of the different Nature paper that we published that cover different scope and different size of applications in science. Famous one is protein folding. You might be aware also of our recent effort in controlling plasma fusion. But also more recently, which I really like, these applications of AI to fill in the gap in Greek documents in ancient manuscript recovery. In terms of the robotics we're doing, we believe that there is like a bi-directional benefit of doing robotics and AI. On one side, we think that artificial general intelligence can be used to bring general intelligence to robots and make them smarter in everyday life. On the other side, we think that robotics can be an embodiment for artificial intelligence, so sort of a domain to generate data, which can be used in a vast number of domains. And before handing it over to Yuval, I just wanted to give you a brief description of the different areas of application that we have. As Yuval will discuss a lot about and present recent results, we invest a lot in simulated embodiments through MuJoCo in order to learn and evaluate our policies in an embodied environment. But we also care a lot about bigger robots. That's why we are here. We're sponsoring this conference. And we have two main pillars of application in real robotics. One is manipulation, and the second one is like locomotion. And we'll briefly talk about the first one. We also think that robotics brings in important challenges that need to be addressed with core algorithms and algorithmic advances, especially in the area of data efficiency. So we also contribute in that area, and Yuval will talk a little bit about that. And last but not least, something that is very dear to me, benchmarking and evaluation and testing our algorithmic advances at scale on real hardware, simplifying as much as possible the experimental workflow for the users. And this is something I will mention briefly later. And then I hand it over to Yuval for the next part.
Thank you, Francesco. So last year, I stood in front of CoRL and I told you that DeepMind acquired MuJoCo and we intend to make it open source. This happened in May of this year. It's open source under a permissive license. It builds to multiple platforms. This is a real, let's do a loopy thing because this is a really cute video. This is a real open source project. We accept external pull requests. We are developing it. This is not a code dump. This is a live, community-driven open source project that we are very, very proud to be leading. We have, since open sourcing, added a bunch of new features. I'm only showing you the ones for which there are cool videos. There's vacuum grippers, gravity compensation, and the very general plugin mechanism for which we already have some implementations, like this new kind of belt with a kink, one might say, a kinky belt simulation. Next. MuJoCo is very mature. It has a lot of great features. I'm not going to go over all of the things in these slides. In this slide, all of the bullets. Let me just focus on a few things. We have really good documentation, which we're very proud of. We also have quite nice introductory tutorials. For example, we have this tutorial showing how to do LQR balancing on one leg, which I thought was quite cute. MuJoCo is quite fast. Unfortunately, it's not known for being fast, but that in some ways is our fault, because a lot of people have been accessing MuJoCo through single-threaded Python, which unfortunately gives you only access to one core. If you actually look at the core package, it's very fast. For example, for this is our favorite benchmark. This is a humanoid flopping around on the floor. Notice that we inject noise, and this matters, so the physics cannot warm start. So on a Threadripper, you get 1.6 million steps per second, or more than 8,000 times faster than real time. And yeah, Python at runtime is a problem. And I'll get to that in a moment. So first of all, we have new Python bindings, which are backported to our old DM control stack. Very easy to install. Pip install MuJoCo gives you everything that you need. By having PyBind, we can now unlock access to all CPU cores. However, physics is not enough. A general environment, if you think about RL, you need rewards, you need game logic, etc. We are working on something along those lines. In the meantime, there are really great open source alternatives. If anybody here uses envpool, we like envpool. But we still support our old, well, it's not that old, but it's very powerful Python infrastructure. In particular, PyMJCF and Composer. These are the two packages that are built on top of MuJoCo that let you compose different, procedurally compose different elements and add, kind of game engine logic like rewards, terminations, etc. For example, our locomotion framework has several composer-based entities like Arena and Walker that let you do something very nice, like with literally 4 lines of Python code. You say, give me this Walker, put it in the Arena, which, as you can see, has some sampled parameters, create a task, and then you have an environment which you can very quickly solve, and you can get this cute humanoid trying to walk around there. So it's, I apologize for the frame rate, by the way. That's a limitation of Zoom. Here it looks much better. So these are still very, very powerful, but we are working on something based on C++ that will replace them. Hopefully, we will have something by the end of the year. So let me tell you a little bit about some of the abstract environments that are already available for everyone. By abstract, I mean that do not correspond to a real robot. First of all, a big shout out to a whole bunch of third-party environments based on MuJoCo. These are 3 that we love. There are quite a few of them: MetaWorld, RoboSuite, and the quite amazing IKEA assembly package. But we also have quite a few of our own, starting from the very, very basic and classic control suite, which has been used in many papers as a simple benchmark for continuous control. We have support for motion capture and skills research. This is an example of work that culminated in the catch and carry paper. So you see this is motion capture on the top right of a person holding a box, and around here on the bottom left, you can see this simulated character walking around from place to place and picking up the box and taking it from platform to platform. So this is everything that was used in this paper is open source, and you can use it yourself. Here is a lovely culmination of this work. Here you can see a kind of overlay of dog motion capture in the beginning. Let's see this. This is the dog motion capture. This is the simulated robot, and this is the real robot. We're kind of fading between the three instances, which I think is very beautiful work. We support embodied multi-agent work, starting from this ant soccer work in 2016. There was an evolution via these, I forget what we call them. Do you remember what we call these little guys?
Box head.
The box heads. Yeah, we've got these box heads rolling around, and this culminated in this beautiful paper that was, I think, published in, was it Nature this year or Science?
Science.
In Science.
Sounds robotic.
Of humanoid soccer with some really amazing emergent behaviors. I recommend looking at this paper. It's quite impressive. Moving on, MuJoCo is actually quite good at supporting biomechanical models. I don't know how many people in this crowd care about biomechanics and neuroethology. We care about this a lot, and we're going to be shipping several really amazing biomechanical models this year. Stay tuned. And now, am I switching over to you?
Yep.
A little bit.
I'm taking over to give you a little bit of an idea of the real robot tools that we have been open sourcing within the scope of MuJoCo for enabling research suitable for this community. So a recent release, which was presented also last year, is what we call MoMA, a modular manipulation environment. It's an environment API built on MuJoCo, and it uses composers that Yuval just introduced. It has a single API for both sim and real, which is a desiderata, of course, which if you want to do your test in sim first and then deploy on the real system. And most of the components that be open sourced, feel free to go to GitHub page and provide your support and help and your comments on the use of the code itself. The idea behind MoMA is to be able to handle different complex environments where you have a lot of different tools, a lot of different sensors and actuators. You have an extreme example of the capabilities on the right-hand side of this slide, where you see 2 arms, 2 grippers, 12 cameras on the gripper, and some mechanisms as well to retract and reset your environment, which is an important component of what we do in reinforcement learning. This is a slide to represent how the API looks like. It exposes the standard environment API that you might be familiar with. So you can send actions and receive rewards and observations back. The actions can be wrapped around the action spaces. Those are coordinated action layers that allows you to do Cartesian control and similar coordinated behavior. And similarly, you can process the sensors that you're getting from the real robot in order to compute reward, terminate your episode, or process observations in order to create abstract observations on top of it. And as I was anticipating earlier, you can do that seamlessly with the same API also on the real robot, so that we can switch as easily as possible between sim and real. Something that is really dear to me, this is something I really care about since I joined DeepMind, is to start promoting a benchmark that can be used initially internal to DeepMind, but now it's available for all of us in order to evaluate how good we are doing in advancing the state of the art in robotics. And I really think that we're missing something solid. And I'd be happy to talk with all of you about your ideas of how we can modify what we have, how we can agree on something that can be used by the community in order to get benchmarking across all the community in order to evaluate what we're doing. What we proposed, it was a relatively small task, and there's definitely not the diversity that Vincent was proposing and probably is missing, but we need to do that and start with something simple. This is the stacking environment. It's called RGB stacking. The task is simply to pick up an object and stack on the top of another one with a distractor object in the playground. What is interesting about that, and I think it might be a value of this particular work, is that there's an entire parametric family of objects. They are really diverse, and they've been designed adversarially to make the stacking really difficult. And believe me or not, this is still a difficult task. We use it as a standard benchmark, but it's sufficiently difficult to keep our research going. You probably have seen this used within Gato. This was mentioned before. But the family is very rich. It's an entire family of parametric objects. We sampled a few of them, 152. We defined an evaluation triplet and a set of other objects that can be used in training. And there are 15 different deformations from a cube object, which is the seed object, deformed into very adversarial objects that are relatively difficult to either grasp or stack on top of. I think it's an interesting first step in the direction of benchmarking. And this is now available to you if you want to use it. It's built on top of MuJoCo and MoMA. It's on GitHub as a simulated environment. There's also all the documentation you need to make a copy of your own copy of the setup and use it for your experiments. It also comes with pre-trained networks that you can use to generate good data and use that data to do something maybe more complicated than just stacking. And last but not least, within MuJoCo, we also released what we call the MuJoCo Menagerie, which is a set of VR robots that are really high fidelity for simulating the robots that you're probably using in your lab in these days. And then I can hand it over to Yuval for the last part of the presentation.
Thank you, Francesco. I'm going to go back one slide. I want to say something about this last bullet here. We in the simulation team, we really care about high fidelity models. And one of the things that we intend to do in 2023 is release a system identification toolbox so that everybody can use the best possible model that they can. And of course, all models are bad, but there's no reason to use models that are worse than they have to be. So let me talk a little bit about agent-side tooling. We have a few really nice open source projects. I think Acme is a great example of an agent-side open source project. It is both a collection of RL agents and a collection of baselines. It's completely open source and well supported. It has a very beautiful design such that you can you can kind of see the classic environment agent design, but it's designed in such a way that going from single machine to distributed machines is almost trivial. So you can start by working on a single machine and then add more machines if you can and if you want. And we really love it. We have quite a few different agent algorithms, both continuous and discrete, and for imitation, offline RL, model-based things. It's a very powerful framework that we use ourselves, and we encourage you to use it. We will help you. Do I have time? We have a little bit of time. Finally, this is a very new thing that we released just last week. I wonder if I should show you the video or if I should just run the demo on my laptop. I think either way, you're not going to get great frame rate. So this is basically a pure model-based MPC package that can be used in the learning context. It can be used to very, very quickly generate expert data. It can be used for task design, and it can also be, you can also use the code inside the learning itself. I see what you're seeing. It's just horrible frame rate. I really apologize for that. And one of the nicest things I think about this package is that even though we do implement some of the classical algorithms like ILQG, which are quite elaborate optimization algorithms, we also implement some really, really simple sampling-based methods. What you're seeing here, this humanoid that you're seeing here, this is real-time screen capture from a laptop. All of this behavior, and you can see it's completely interactive, is implemented by basically a very trivial sampling algorithm. So personally, I'm hoping that the simplicity of these algorithms will lead to the, let's call it the democratization of predictive control and the integration of predictive control with learning methods, which I think is going to be straightforward and very powerful. And if you want, you can come and talk to me about this later. And do we have any more slides? I think that's it.
Yep, we are ready to take questions.
Ken.
You say more about the system like these, you say a package. What kind of system like these, for example, even in those examples that you're looking at stacking, there's so many parameters in this period. You're looking at friction, mass, what are the frontiers?
I think it's going to be completely general. So any parameter that you can put in a MuJoCo model, I will be able to give you the value of this parameter that makes the model best match your data. Will that match be a good match? I don't know, but it will be the best match I can give.
I can give you a bunch of real data. You don't choose the parameters.
Yeah, exactly.
Other questions? Don't be shy.
How about deformable material?
Yeah, that's probably difficult. Are you asking about identifying deformable materials or about simulating deformable materials? I mean, you're not going to be able to identify them before you simulate them. We've started, as you saw with that little belt clip that I showed before, we've started going in that direction. But, you know, MuJoCo really tries to be in a sweet spot of simulating things fast. And if we can't do it fast, we're much less excited by it. So we're really trying to, find the right parameterization to get soft bodies. That's the main reason that we started with one-dimensional soft bodies, cables and belts, because if there's any kind of soft thing that you could simulate, you could simulate fast, it would be those. Look, it might be the case that if you want fast simulation of soft bodies, a traditional simulator is just not what you want. We're looking into it. This is one of the main reasons that we introduced the plug-in mechanism. It's so that we could try out different things before we decide to adopt them officially.
Yeah, and if I can follow up, actually, we already started the integration within MuJoCo of a NERF model. That is a paper that we published recently. And I think that's a very promising direction. Next step, considering what we're doing at DeepMind, probably learning simulations and the transition model for the state space will be an interesting next step. And as Yuval was mentioning, we are thinking about plugins that would be suitable for doing that and matching that with a simulation state of the MuJoCo environment. So it's actually quite an interesting research direction.
Are you planning on, or do you have GPU support to parallelize the simulations, the physics of it?
No. And I'll give you the long answer. First of all, from everything that we've tried, if you have a good CPU, you're very competitive with any GPU simulator out there. So one answer is just get a good CPU. The other answer, which is a bit more tricky, has to do with the way code looks like when written to the GPU or TPU or any kind of accelerator. You're forced to rewrite your code in a way that makes it much more difficult to understand, much more difficult to maintain, and usually binds you to a particular platform. I think the only way to write code to accelerators that does not bind you in that way is by using something like JAX. And indeed, Brax is an amazingly fast simulator written by our friends in Google. We love Brax. It's very, very impressive. But if you look at Brax, there are trade-offs there. Like, in order to get that speed, you give up a lot of things. In a word, it's very difficult to get branchy code. Branchy code is not easily parallelizable. And in Brax, indeed, it's much harder for them to do things that for us are very easy to do. So we prefer to leave our code readable, easily compilable to multiple CPU platforms, maintainable. I think we'll be able to push the code forward much faster by staying on the CPU.
Another question over here, if you can bring the microphone.
So I guess like following up on both of what you just said, like, have you thought about then like incorporating maybe learn models with the simulator? And then if you were going to incorporate learn models, and sometimes you would probably want GPU acceleration, so then that might get messy too. So have you thought a little bit about that?
Absolutely, yes. Yeah, one of the beauties of simulating on the CPU is that your GPU is free. So one thing your GPU can do is render. And we are working on a very, very fast renderer, which is something that a lot of MuJoCo users care about. But the other thing that you could do on the GPU is simulate things that are not easily simulated with MuJoCo. For example, if you want to simulate something like a robot folding a t-shirt, I would say simulate the robot in MuJoCo and simulate the t-shirt in something else for which a GPU type architecture is perfect. That's exactly what you want to simulate something as, with so many similar degrees of freedom like a soft body. And I do think that that's the right direction to go. I think I'll stop there. I have more to say about that, but come to me later.
Well, I just as a follow-up, I think looking at the entire system of your experiment, not just one particular bit like the simulation environment, but the system as a whole and the different components that are interacting is really important to understand where you want your code to run. And this is basically where Yuval was heading to. Like, you need to think where the GPU is useful and where the code will be readable, and then we can, think about the entire system as a whole system with the CPU as well and different threads and so on interacting together. Well, get in touch. We'll be around, and we are happy to hear more feedback on the tools that we develop. Thanks a lot.
Thank you.